let's talk some more about multiple integration. We're going to discuss both double and triple integrals. And first of all, let's remind ourselves that if we're talking about double integration, our happiest situation, the luckiest situation in rectangular, is if you have x limits that are constant and y limits that are constant, so that you can take your double integral and simply write it either as the integral of f from c to d with respect to y and a to b with respect to x, or vice versa. A to b because that's x on the outside, and c to d because y is on the inside. Perfect situation where you have your domain of integration and constant limits of integration. But suppose you don't have a nice, neat rectangle. Suppose you have a more elaborate region of integration. Well, either x goes from a to b as y varies from a lower function, which I'm calling L of x because I'm avoiding f and g. F and g are busy doing other things, all the way up to an upper function, u of x. So x goes from a to b, and y goes from lower function of x to upper function of x, and that's how your integral will be set up. Contrary to that is the one where c and d for your y limits are constant, and it's more convenient to express x as a left function of y and as a right function of y. So you will integrate with respect to x first to get the L of y and R of y into your integrand, and then finally you integrate with respect to y because y is the only variable left. That's the basic business of rectangular coordinates. There's less complication with polar coordinates. If you're lucky and R is a constant A and a constant B, those are concentric circles centered at the pole. And if theta is a constant, alpha for one ray and beta for another ray, you're simply getting a domain of integration that is a sector of an annulus. And so when you integrate that, you're going to be looking at constant limits of integration. The order won't really matter. On the other hand, sometimes you have a situation where theta has two constants of integration. Okay, they almost always do, the constant limits of integration. And R is some inner polar function. Okay, that's the lower limit of integration function. And you have the upper limit of integration function. And so in that case, you would be looking at, let's say we're using G for our integrand with respect to A. Don't forget that's R dr d theta, and practically all double integrals in polar coordinates have alpha and beta on the outside for theta, and possibly functions for R. And of course, if your integrand was written in terms of x and y, you have to convert that into polar as well. Now let's switch over and talk about what we would do if we had a triple integral. If you have a triple integral of some function x, y, and z with respect to dv, and let's call our region E because our textbook likes to use E for three-dimensional regions. You already know, at least I think you know, that dv is going to be dx, dy, and dz. Now, a lot of textbooks and a lot of instructors make a big fuss out of the fact that depending on who you pick for the first and the second and the third differential of integration, you can write this 6 different ways. But in reality, that's almost never a problem. This is what usually happens. You have your three-dimensional system, and somewhere in the xy plane, you have the base of your region. Okay? And let's say it's D. And I've written it so the D is in the right orientation for a label lying on the xy axis. And so here's my z-axis. And let's suppose that this is the base of your region of integration, and E is topped off at the top by some function, and we'll just call it G will be useful, okay? G of X and Y. You can almost always rearrange things so that this region is described in the following way. First of all, you have D, and D is going to be, well, maybe X goes from A to B. It might be Y going from C to D. It kind of depends. And then Y is going to go from your lower limit of integration to your upper limit of integration. So if you can take care of describing this region, the last part is E, because this is just the D part. And for the E part, you just need Z. How are you going to do that? Well, Z will go from, this case, I'm going from 0, from the xy plane, up to whatever this function is, G of x, y. It's possible to have a function g1 and a function g2 and be sandwiched in between, but I don't want to be that complicated right now. So let's do this. Triple integral over the three-dimensional domain of integration E of this function, xyz, dv will be the integral from A to B. The integral from whatever these guys are, lower function of x to upper function of x, and then from 0 up to g of xy, and then we have our integrand, whatever that happens to be, and this is going to be dz, dy, dx, and we had just barely enough room to do all of that, okay? And I tell you again, any problem can be rearranged so that z depends on x and y. You can permute the labels, you can relabel things, and make it work that way. So here is E. It's this big cylindrical chunk in this illustration, and this is a triple integral. If my integrand is a density function, I would be finding the volume, the mass of this guy. Okay? So if I had a density function that was in grams per cubic centimeter and my units were centimeters, I would find how many grams the whole thing weighed. A simple example would be something like a paraboloid. So let's take a look at a paraboloid. And we'll do a simple example because I don't want to do anything too complicated. I might mess it up. So here's the circular base of my paraboloid. So there's my region. Let me tell you a little bit more about it. My paraboloid is going to be 4 minus x squared minus y squared. Okay? So this will be 4. This will be 2. This will be 2. This is my region. Okay? And just for fun, I'll put in a density function. I'll pick something simple. I'll just pick z. Okay? That's not a very good density function. It says that the density of my paraboloid is 0 at the bottom, so it's pretty flimsy. And up near the top, it's 4. So this gets denser as you go up. But I'm not looking for trouble. This is just a simple example. How are we going to do this? Well, if you look at the base is just a circle of radius 2, d. So x would go from -2 to 2. And y would go from the square root of 4 minus x squared, that's minus 4 minus x squared. The top is the semicircle. Y is the square root of 4 minus x squared. And down here for the bottom, it's the negative of 4 minus x squared. And then finally z simply goes from the bottom to the top. That's my description of E. So what would my mass be? Well, my mass would be the triple integral over E of my density function with respect to volume. So in this case, minus 2 to 2 minus square root 4 minus x squared up to 4 minus x squared, 0, 4 minus x squared minus y squared, z, dz, dy, dx. You don't want to do this in rectangular. You want to do this one in polar, except when we go three-dimensional with a polar coordinate system, we basically do r and theta for the base, and we just add a z-axis to it. So then we have dv is going to be r, dr, d theta, dz. That's how we go three-dimensional on this. And m, in this case, see if you can follow me on this, 0 to 2 pi, because you're going to go all the way around the circle, 0 to 2, that's the disk, that's d, all taken care of, 0, 2, 4 minus x squared minus y squared, that's minus r squared. And here's z, and careful, r, dz, dr, d theta. Notice I needed to move the z up to match the limits of integration, okay? And if you work this out, what's going to happen? Well, first of all, you integrate z, so you get z squared over 2 from a 0 to 4 minus r squared. Okay? The r is left over, the dr and the d theta. 0 to 2 pi, 0 to 2, 1/2 4 minus r squared r dr d theta. Okay. Now, there's something you might notice here. I left off the square, okay? So that was a mistake. That has now been corrected. And what's the derivative of what's inside? The derivative of what's inside, if you let u equal 4 minus r squared, du would be minus 2r dr. We have an r dr. We don't have the minus 2. So I could go from 0 to 2 pi. Here's this 1/2. Okay, I don't have a minus 2, so I have a minus 1/2 for a correction factor. 4 minus r squared cubed over 3 from 0 to 2 and d theta. So basically I'm doing a u sub. If I go from there, what do I have? Minus 1, let's see, 12th, 4 minus 2 squared cubed. Oh, that's going to be a 0. Okay? And then plus 1/12, stick in a 0, I get 4 cubed. And that's all constant. I still have 0 to 2 pi d theta. That's just going to get me a 2 pi. So I get 2 pi times 1/12 times 64. Okay? So let's see. 2 cancels with this guy, so I've got pi over 6 times 64. I can cancel a 2 out of this, so I have 32 pi over 3. And that will be my answer.